Hello everyone, welcome to Simplilearn's YouTube channel. Today we will be discussing about Kruskal's algorithm in data structure. In today's video, we have a challenging activity for you guys. So stay tuned and do participate in formulating answer to the question that is going to pop up on your screens in next few minutes. But before we begin, let me tell you guys that we have daily updates on multiple technologies. So if you are a tech geek in a continuous hunt for latest technological advancements, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now without any further ado, let's get started with the agenda for today's discussion. We will start this discussion with introduction to Kruskal's algorithm. Followed by that, we'll understand how we can create a minimum spanning tree for a given graph using Kruskal's algorithm. And finally, we will cover the coding implementation of Kruskal's algorithm using disjoint sets. I hope I made myself clear with the agenda. Now let's get started with our first topic, Introduction to Kruskal's algorithm. The Kruskals algorithm is used to find the minimum spanning tree for a given graph. But what exactly is a minimum spanning tree or MST? Well, a minimum spanning tree is a subset of graph G having the same number of vertices as of graph G and edges equivalent to number of vertices minus 1. Along with these properties, it also has a minimum cost for the summation of all edge weights included in a minimum spanning tree. If you want to learn more about spanning trees, then please consider watching our video which you can find in the I button section right away. Now coming back to the Kruskals algorithm, the Kruskals algorithm sorts all edges in increasing order of their edge weights and keeps adding nodes to the tree only if the given edge does not form a cycle. Also, it picks the edge with minimum cost at first and the edge with maximum cost at last. Hence, we can say that the Kruskals algorithm makes a locally optimal choice intending to find global optimal solution. That is why it is also considered as greedy algorithm. The data structure that we are going to use for implementing this Kruskals algorithm is union find. But now you must be thinking, what exactly is this union find data structure and how it works? Well, union find is a data structure that keeps tracks of elements that are split into one or more than one disjoint sets, where a disjoint set is collection of two distinct groups or clusters that do not have single common element. The union find features two important operations named as find and union. The operation find returns the set or group to which provided element belongs. Basically, it constructs a bijection between the object provided and its set, whereas the union function joins two distinct disjoint sets to create a single subset. Let's understand how this data structure works with the help of real life example. Let's say we have some singing magnets placed on table with a higher magnetic affinity towards each other. All these singing magnets present on the table are color coded with sky blue color. Now, due to the high magnetic attraction, the magnets A to E will form a strong magnetic field which will cause the bonding or connection of all these magnets. As a result, all these magnets will be grouped together. We will now color code this set with red color. Along with that, we'll also call this set as red. After that, the magnet F to I are also closer to each other. Thus, they will also form a connection. We'll call this set as green. Finally, this last set of magnets will also formulate a connection with each element inside a group. We will call this group as set purple. All these distinct magnets got distributed into three different disjoint sets. But as the magnetic attraction between these groups increases significantly, hence all these clusters of magnets will end up connecting with each other. This scenario can be related to the union function. Union function merges different sets into a single subset where the find operation helps in extracting the group of element to which the particular element belongs. Similarly, in this scenario, a particular magnet can be traced back to its group with the help of color code that we have maintained alongside the magnets. The use of union find in Kruskal's algorithm can be related to this example. While implementing Kruskal's algorithm, we are going to maintain three distinct disjoint sets. The first set will store edge weight values for all edges in a graph, whereas the second set will store tree hierarchy for a different nodes. The last set will store the ranks for all nodes included in an MST. By using the union find structure and its operation, we can justify the entry of each edge into the spanning tree, which we will explain in the implementation of this algorithm. But let's understand the functioning of this algorithm primarily. The Kruskals algorithm begins with sorting all edges into increasing order of their edge weights. This sorting is done to include edges with the least edge weight primarily into the tree structure. After that, we'll pick the first smallest edge and we'll check if it generates any cycle in the tree structure or not. If it does not form any cycle, then we will include that edge into our spanning tree. Otherwise, we will discard it. We will keep repeating this process until mod of v minus 1 edges are included into our MST, where v is number of vertices. Now moving ahead, let's discuss how we can create a minimum spanning tree using Kruskal's algorithm. This given graph GVE contains 12 edges and 6 vertices, and we are supposed to find out G dash such that the number of vertices is equal to 6 and the number of edges is equal to V minus 1, that is 6 minus 1, which is equal to 5. The one more condition that the formulated structure must abide by is that the summation of all included edge weights must be the minimum possibility for this spanning tree. Going forward, we'll discuss how we are going to create MST for this graph using Kruskal's algorithm. The first step that we need to perform is removing all the loops or parallel edges from our graph. Hence, primarily, we'll remove these two present loops. The next step that we are going to perform is arranging all the edges in increasing order of their weights. The reason behind maintaining the sorted list is to make sure that the first edge for insertion is of a minimum cost. Here, I have maintained the sorted list for all the edges that are part of our graph. So according to this sorted list, the first edge that we are going to insert in our MST is edge EF, as it has minimum weight cost, that is 2. The next edge that we have in our sorted list is edge FD. It also has an edge weight equal to 2. Hence, we'll include it in our spanning tree. The third edge in our sorted list is edge BC with weight 3. The inclusion of this edge does not formulate any circle in our tree structure, hence we'll add it to our MST. The next edge is edge CF, having a edge weight 3. So we'll include it in our MST structure. The fifth edge that we are going to pick is edge CD, having weight 4. But the inclusion of this edge inside our spanning tree will create a loop, and the structure that contains a loop can never be considered as tree. Hence, we have to exclude this edge. The next edge is edge BF, and the inclusion of this edge will also generate a cycle in our spanning tree structure. So we will exclude this edge as well. The next edge is edge BD. This edge has weight value 6. The inclusion of this edge can also create a loop in our structure, so we'll have to discard this edge as well. The next up is edge AB with a weight value 7. Even though this edge has higher weight value than previous edges, but it does not formulate any cycle in our MST, so we'll include it in our tree structure. By doing that, we have generated V minus 1 edges for our spanning tree. Thus, we won't iterate further in our sorted list. This generated MST has minimum possible cost for our graph GVE, which is 17. I hope that you guys have understood the MST implementation process using Kruskal's algorithm. Cause in the next slide, I have a problem for all of you guys to assess your understanding of Kruskal's algorithm. The graph shown on your screen contains 10 vertices and 18 edges. And for this graph, You are supposed to generate a minimum spanning tree such that it contains 10 vertices, 9 edges, and minimum construction cost. In order to do that, you can take out your pen and paper to draw the spanning tree structures based on the step that we have discussed till the time. I'm aware that this graph is quite strangely structured. However, if you can solve this problem, you will undoubtedly be able to solve other difficult problems out there. And of course, if you are confused about any step, then you can reiterate through the session. But here I am going to give you guys a little moment to figure out your answers. Well, now that you guys must be ready with your solution, so let's check if it is true. The highlighted part of this graph is possible structure for a spanning tree with minimal cost. By removing all the edges, the MST will look something like this. I hope you guys have got the right answer. On that note, let's dive further and discuss the implementation strategy for Kruskal's algorithm. While implementing the Kruskals algorithm, primarily we'll generate a C structure for keeping track of the source and destination node along with its weight. After that, we'll sort all that edges of a graph in increasing order of their edge weights. Moving ahead, we'll create three distinct sets to maintain nodes of a graph, their hierarchy in tree, and corresponding ranks for every node. For each insertion of an edge in MST, we'll update the rank and parent of each node. If the two nodes have the same parent node, then we will not insert the edge joining them, as it will generate the cycle in tree structure. Let's understand all these steps with the help of an example. This is the graph structure for which we'll try to generate a minimum spanning tree using C programming language. As discussed earlier, primarily we'll create a sorted list of all edges in increasing order of their edge weights. The list will contain the source node, destination node, and corresponding edge weight for that particular edge. Along with that, we are going to maintain disjoint sets to carry out union operation. Those disjoint sets are parent and rank, and they will include rank value and parent value for every node in our graph. Initially, all the nodes are in their own different sets. Hence, we'll set their parent values to -1. Also, the ranks for these nodes will be initialized to 0 at the beginning because we haven't included them in our minimum spanning tree. Having said that, let's include the nodes of our graph in our MST. In upcoming slides, we'll traverse through our list of edges to include them in our minimum spanning tree. Now, the first edge that we are going to check is edge DC, which have minimum edge cost, that is 1. In order to insert this edge in our MST, we'll need to find the absolute parent of node D and C as well. So let's check out the parent set to determine the absolute parent value of node D and C. The parent value of node D is -1 and parent value of node C is also -1. Both of them are having same ranks, which means either we can make node D point to C or node C point to D. Here, I'll assume that node D points to node C. So, if node D is pointing to node C, then the parent of node D will become node C. And as C becomes the parent of node D, the rank of node C will change. Remember, whenever two disjoint tree structures are joined together, then the rank of one being pointed to will increase by 1. Hence, the rank of node C will become 1 now. Once the disjoint sets are updated, the union operation will generate the link between node D and C. Now, we'll process the second edge in our list, that is edge CB having weight 2. Primarily, we'll check the parent values of both these nodes. Node B and node C have parent values -1 and -1. which indicates that these nodes are absolute parent of their own sets. Since they have different absolute parents, we can join both of them. However, the rank of node C is higher than node B, thus the connection should point from node B to node C. As node B is pointing towards node C, thus node C will become the parent of node B as well. Hence, we'll update the corresponding absolute parent values for them. Next up is edge BA with the weight value 2. Now the parent value for node A is -1 and the parent value for node B is C. So both of them have distinct parent value, which implies that we can establish a connection between them. For that purpose, we'll have to update the rank field. And as the parent of node B is node C, the rank of C will definitely increase by 1. Once the fields are updated, the edge will get included in our MST. On that note, we have generated our minimum spanning tree, but you must be thinking about how our algorithm will discard the other edges. So to understand that, we'll traverse further in our list of edges. The next edge is edge AC, and the parent of node A is node C itself. Hence, we'll discard this node as well. Now the final edge in our list is edge AD, and again, both these nodes have the same parent node. Thus, we'll discard this node as well. Now, you must be thinking about how we can limit iteration of the whole list if we formulate MST using the few topmost edges only. Well, the answer to that is pretty straightforward. We can avoid the complete traversal of the list by using looping condition from e is equal to 0 to e is equal to mod of v minus 1. When we use this condition, the looping will stop when v minus edges get included in our MST. Now the next up is the time complexity analysis of Kruskal's algorithm. The time complexity of Kruskal's algorithm will be big O of E log E plus E log V. The E log E for sorting all edges and E log V for finding the edge from maintained 3 sets. The average time complexity graph for this implementation will be something like this. It will be of parabolic nature. I hope that you all have understood the strategy for implementing Kruskal's algorithm. So, without wasting any time further, let's visit the code editor to develop a program in C programming language for Kruskal's algorithm.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Now, to begin with coding implementation, the first thing that we'll do is we'll create a storing system to represent a weighted age. For that purpose, we'll use structure in the C programming language. So let's get started with that. Struct age, and inside this structure we'll create int source, destination, and weight. Now what we'll do is we'll utilize this structure to store the edges of the graph. Moving ahead, we'll also initialize the structure for storing the complete graph. So let's create one more structure and we'll name the structure as graph, and inside this graph structure we'll create node. We'll also create variable e to represent number of edges in our graph. We'll also call the reference of structure edge to this graph. By doing this, we'll be able to include all the edges into our graph structure as well. So let's create that reference struct edge star edge. Now we have successfully created the structure for graph. Now moving forward, what we'll do is we'll assign dynamic memory to the reference of graph structure. For that, what we'll do is we'll write code struct graph star generate graph, and inside this function we'll pass int node and the number of edges, that is e variable. Now we'll write body for this function, and inside body, first thing what we'll do is we'll create the space, that is dynamic memory space for this graph structure, equal to struct graph star malloc size of struct graph. Next, graph dot node will be equal to node and graph dot number of edges will be equal to e itself. Next, what we'll do is we'll allocate a memory to each edge. Okay, add an underscore here. For that, what we'll do is we'll use struct edge star malloc size of struct age, and finally we'll return the graph. Now we have successfully allocated memory space to our graph and individual edges as well. So moving forward, what we'll do is we'll initialize one more structure to store the parent array and rank array. Basically, these are the disjoint sets whose usage will allow us to generate a spanning tree using union find algorithm. So let's get started with that. We'll create another structure and we'll name this structure as tree underscore maintenance underscore set, and inside this structure we'll create parent array and rank array. Now we have created the tree maintenance set structure, so let's generate an union find algorithm for maintaining MST structure. In order to do that, let's create a function named find disjoint set first. So this find disjoint set function will be of int data type find underscore disjoint set, and inside this we'll pass struct tree underscore maintenance underscore set, and its object subsets and a variable int I. Inside this function, we'll use if case to find root and make it as a parent of argument I. Also, if it is -1, then we'll need to update it. For that, we'll keep recurring through this if block by calling the function find disjoint set inside if block. So let's do that. If subsets I dot parent is not equal to I, then what we'll do is we'll get inside this if block and we'll execute subsets I dot parent is equal to find underscore disjoint set, and we'll again pass same argument subsets comma subsets I dot parent. And finally, we'll get out of this if block and we'll return subsets I dot parent. Now we'll create a function for union operation. Let's name this function as void union underscore disjoint set, and inside this we'll pass struct tree underscore maintenance underscore set and its object subsets, and we'll pass argument x and argument y. Now inside this function, we'll create two variables named xroot and yroot. And the xroot variable will store the return data from find disjoint set when the x has been passed to the function. And similarly, the yroot will store the return value for find disjoint set given y as an argument. So let's write command for that. Int xroot will be equal to find disjoint set, and objects will be subsets comma x. Similarly, int yroot will be equal to find disjoint set and object subsets and variable y. Now, in order to build connection between these nodes, As discussed previously, the node with lowest rank value should always be pointing to the node with highest rank value and vice versa. So we'll have to use this if block in order to put this condition in the connection building block of our program. So we'll write condition for that here now. If subsets xroot dot rank is greater less than subsets yroot dot rank, then what we'll do is we'll set subsets xroot dot parent to yroot. That means, oh, okay. So what we are doing here is we are checking the rank value of xroot. If the rank value of xroot is smaller than yroot, then what we'll do is we'll simply set the yroot as parent of xroot. I hope you guys are clear with this. Now moving forward, we'll write else if part of this condition, else if subset xroot dot rank, sorry, I'll have to add s here, and if subsets xroot dot rank is greater than subsets yroot dot rank, then what we'll do is we will set subsets yroot dot parent is equal to xroot. Otherwise, if both above mentioned condition fail, then what we'll do is we'll add one more condition. We'll set subset yroot dot parent to xroot, and then we set subset xroot dot rank to incrementation. There is one mistake over here. Subsets, okay. So now we have implemented the union find algorithm for this Kruskals implementation. Next, we'll create a function to sort the list of edges in our graph according to increasing order of their edge weights. So let's create new function for that. We'll name this function as int my comparator, and inside it we'll pass const void star a and const void star p, and we'll create function body. But before we get started with coding implementation of this myComparator function, I want to talk about arguments of this function. So basically, A and B are constant quantifiers. The significance of this quantifier is to tell the user that you cannot modify this pointer and the location it is pointing to throughout the program. So let's get started with the coding part of this myComparator function. What we'll do is we'll create struct age star a1 is equal to struct age star a semicolon, and similarly struct age star b1 will be equal to struct age star b. Next, we'll return the output a1 dot weight is greater than b1 dot weight. So basically what this statement will do is, if the weight value of a1 is greater than b1, then it will return a1 as output, and if the weight value of b1 is greater than a1, then it will return b1. I hope you guys are clear with this myComparator function. So moving forward, we'll finally create a Kruskal MST function. The return type of this function will be void, and we'll name this as Kruskal MST, and inside it we'll pass argument struct graph star graph, and we'll create function body. Now the first thing that we'll do here is we'll assess the value of number of nodes in a graph, and after that we'll generate a new reference of structure age for storing our MST. So the first thing we'll get the node to graph dot node and struct age result node. Along with it, we'll also initialize variable e and variable I equal to 0. So int e is equal to 0 and int I is equal to 0. We'll need to break the indentation here and here as well, and semicolon. So basically these variables will store index values for result and index variable for the sorted list simultaneously. Now moving forward, we'll sort all the edges of a graph. If we are not allowed to change the given graph, then we can create a copy of the given graph. The function named qsort allows us to do that. So let's create that qsort function here. Qsort graph edge comma graph E, comma, size of graph. H 0. So this qsort is nothing but C standard library function that implements a polymorphic sorting algorithm for arrays of arbitrary objects according to a user provided comparison function. And that comparison function is nothing but this my comparison function. And I guess you guys must be clear with this qsort term. So let's add comma here and we'll give call to a my comparator function. Now moving forward, we'll break the indentation and we'll call the object of tree maintenance set underscore maintenance set star subsets equal to struct tree underscore maintenance underscore set star malloc node star size of struct tree underscore maintenance underscore set and we'll add semicolon here. So next we'll create subsets equal to number of nodes, and after that we'll make sure that all the elements have the rank value equal to 0, and to do that we'll initialize new for loop. So let's create for loop here. We'll begin it from v is equal to 0 to v is less than node, and we'll set this v to incrementation. After that we'll make body for this for loop, and inside it we'll set subsets v dot parent is equal to v and subsets v dot rank is equal to 0. Now moving further, we'll traverse through all the edges in the graph, but we want to limit our traversal to the number of vertices minus 1, and to achieve that we'll create while loop here. While e is less than node, capital node, then node minus 1, and I it's smaller than graph e then create struct age next underscore age equal to graph dot age I plus plus, and here we'll create x and y nodes. So let's do that. Int x will be equal to find underscore disjoint set, and we'll pass subsets comma next age dot source, and for y we'll pass find underscore disjoint sets subsets comma next underscore edge dot destination. Now if including the age between x and y does not create the cycle in our graph, only then we can include that age in our MST. For that, what we can do is we'll set if x is not equal to y, then we'll set result e plus plus equal to next underscore edge, and we'll find union disjoint set for subset, and we'll pass x and y as well. With this, we have successfully created our Kruskal's MST function. Now what we'll do is we'll also print the structure of our minimum spanning tree. For that, we'll need to create pattern using printf function. So let's do that. The first statement that will print on screen is ages created in MST are as below, and we'll add \n so that our output gets to the next line. We'll add semicolon, and to that we'll add int minimum cost variable, and we'll initialize it to 0. So okay, so what we'll do is we'll create for loop here, and we'll initialize it with iterator element beginning from 0 till I less than equal to e, and we'll iterate this I element. And what we'll do is we'll create pattern for printing the edges. The pattern will go like modulus d dash dash modulus d equal to modulus d slash n, and The parameters that will get printed will be result I dot source comma result I dot destination and result I dot weight. Okay, so we haven't added comma here. Now this error will get resolved. Now after this, what we'll do is we'll increment this minimum cost variable by adding the values of edges to it. So we'll take this minimum cost variable and we'll add result I dot weight to it. Now we'll get outside this for loop and we'll printf one more statement. The cost for creating MST is modulus D and we'll print minimum cost. Okay, we have now successfully implemented Kruskal's algorithm function and we have created code for printing it on console as well. So now moving forward, we'll work on our driver method, and for that let's get into its function body. Here first we'll define the number of nodes that we are going to use for our graph. Those number of nodes are 4. The graph structure that we are going to pass to this Kruskal's algorithm program is the same that we have discussed implementation strategy for. It had 4 edges and it also had 6 edges as well. So we'll add 6 edges here. Now what we'll do is we'll set struct graph star graph equal to generate graph and we'll pass node comma e and we'll add semicolon. Now next we'll create graph structure by implementing the edges. So the for first edge we'll call graph dot edge 0 dot source will be equal to 0. That means the first edge will begin from 0 and it will end at destination node and that will be 1, and the weight for this edge will be equal to 2. Now we'll copy this pattern and we'll paste it below. Okay, and now the age will be 1, and for this age 1 the source will be 0 and destination will be 2 and the weight value will be 4. Now let's copy this again. We'll paste it and we'll set age number to 2. We'll change source and destination now. Source will remain same and destination will be changed. We'll make it 3 and the weight value will also remain the same. That means age between 0 to 2 and age between 0 to 3 have same age weight. Now for next, Control V, we'll remove this indentation and now we'll change the node number, age number. Here the source will be 1 and destination will be 3 and the age weight value will be 3. After this we'll add new age. The age number will be 4 now. The source will be 2 and destination will be 3 and age weight will be 1 and the last age will be age 5 and the source will be 1 here and destination will be 2. The age weight will be 2. Now after this what we'll do is we'll give call to our Kruskal MST function in order to generate minimum spanning tree and we'll pass this graph structure to it and we'll add return 0 statement. With this, we have successfully completed our programming implementation for Kruskal's algorithm. So let's run it and check if our code is working fine or not. Okay, so we are getting 3 problems here. The first one is expected token. Oh, so int node will be equal to graph.node. And this node should also be capital here. Okay, so what next error is there? Yeah, so now our code is bug free. Oh, but some exception is happening here. We'll jump this exception. We'll try to jump it. Okay, but we are not having any errors into our system, so I think that's the compatibility issue with our VS Code. So let's copy this code and paste it into the virtual coding environment and we'll check it if this code is working fine or not. So we'll copy the code and we'll go back to the Google Chrome. We'll go to the online compiler tool, and here we'll paste our code and we'll run it. Okay, so here we are getting our output. So there will be only 3 edges that will get formed in our minimum spanning tree, and the cost for all those edges will be 5. I hope this coding implementation is clear to all of you out there. If you're concerned about this code, then don't be, as we can send it over to you if you drop your email IDs in the comment section below. So drop your email IDs in the comment section below in order to receive this code. So with this, we came to the end of this video. I hope this video on Kruskal's algorithm was informative. If you have any queries regarding this topic, then let us know about them in comment section below and we'll surely get back to you. Thank you so much for being here and do watch out for more videos from us. Until then, keep learning and stay tuned to Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.